Hello everyone, welcome to my channel. In the last video, we discussed and implemented transformers architecture from scratch in PyTorch, the architecture that is useful for natural language processing. But I left you with one question. Can the same architecture that we use for text can also be used for images? Can the transformer that reads sentences can also see the images? And Google answered that question in one of their paper. That is, a transformer is worth 16 by 16 words. And the answer was yes. Today we are building the vision transformer, and the good news is if you have watched my last video, 90% of it is already covered. We have already discussed positional encoding, layer normalization, residual connection, encoder architecture. The difference in this paper is, or in this video that we are going to cover, is how to convert that image into sequences and the spatial flag that we use at the classification step. So let's dive into it. Before we write a single line of code, let's understand why vision transformer exists. What problem was it solving? For decades, convolutional neural network or CNNs were the gold standard for computer vision, like ResNet, VGGNet, EfficientNet, all CNN based, and they worked extremely well. So why did we need a transformer? CNNs have a fundamental inductive bias baked into their architecture, that is locality. A convolutional filter looks at a small region of the image at a time, in this case a 3x3 patch, to understand long range relationship in an image, like how the top left corner relates to the bottom left corner. A CNN has to stack many layers so information can propagate across the image gradually. This works, but it's slow and expensive. The transformer, on the other hand, has no bias. With self-attention, every patch can directly attend to every other patch in a single operation. Long-range dependencies are free. And as the vision transformer paper showed, when you train on enough data, removing that locality bias and letting the model learn spatial relationship from scratch actually produces better results. And there is a second advantage as well. CNNs require specialized architecture for vision. You cannot use the same model for text and images without significant redesign. Vision Transformer unified this in one architecture that works for both text and images. And today we are extending our transformer from the last video to handle images. We won't be changing the core architecture at all. So let's dive into the core idea. Here is the key insight of the entire paper. If you look at the diagram, this was taken from the paper itself. The transformer processes sequences. Words in a sentence are sequence. So to use a transformer on an image, just turn the image into a sequence. How? Cut it into patches like these. Take a 32 by 32 pixel image, divide it into a grid of 16 by 16 patch. You get 4 patches, a sequence of 4 elements. Now treat each element or each patch exactly like a word token. Flatten it, project it into a dimensional vector, and feed the sequence into the transformer encoder. That's it. That's the entire trick. The paper title, "An image is worth 16 x 16 words," is literally describing this. Each 16 x 16 patch is treated as one word, as you can see in the image as well. Once you have that sequence of patch embedding, everything else is exactly the transformer encoder from the last time. Self-attention, or either be it feed-forward neural network, layer normalization, or residual connections. And the model doesn't even know it's looking at an image. It just sees a sequence. Let's now move on to our coding file, and we will start with the imports. So here I have created a simple vit.py file to create our transformer or vision transformer. Let's start by importing the libraries and classes. Let's start by a simple import torch, and then it will be import torch.nn, torch nn functional, and there will be an additional import this time, that is torch vision dot transforms as t, and we will import the Adam optimizer, torch dot optim import Adam. And since we will be testing it on MNIST dataset, so we will import that as well. Torch vision dot datasets dot MNIST import MNIST. And we will also import the utility function for loading the data, that is data loader, and two more libraries, math and import numpy as np. After that, we will again set the manual seed to 42, so that whenever we initialize the random weights, we always get the same weight on each every cycle or every epoch of the initialization. And then we will have few constants like dimension of the model. This time it will be 64 because we are testing it on MNIST. Then number of classes for classifying. Oops, sorry about that. Yeah, number of classes. This will be 10, 0 through 9 for the 10 digits in MNIST. Image size will be 32, 32. We will resize the MNIST dataset from 28 cross 28 to 32, 32. Patch size will be 16, 16. And number of channel, that will be 1, since it's a black and white grayscale image, so we won't be needing RGB channel. And this number of heads will be same from the previous video, which is 8, as the transformer uses 8 heads. And number of layers will also be equal to 6, same as the transformers video. And batch size will be equal to 128, and epoch we will be training it for will be 10. And for now, let's keep the learning parameter, which is the hyperparameter learning rate, to 0.005. We'll tweak it as per the result. Okay, I think this is all for the imports. Let's move on to the next one. Now, the first thing we need to build is the patch embedding layer. This takes a raw image, as you can see here, and it converts it into a sequence of vectors, one vector per patch. There are 2 steps for doing so. First is splitting the image into patches like these, and then linearly projecting each patch into the model dimension, or the dimension of the model. You might think we need to manually slice the images into patches and flatten each one and then run a linear layer. That would work, but there is a much cleaner way. We can do both steps simultaneously using a single nn.conv2d layer. Here the key insight, a conv2d with the kernel size equal to patch size and stride equals to patch size, meaning no overlap between windows, slides across the image exactly once per patch and applies a linear transformation to each patch. If we set the number of output channels to dimension of the model, then each patch gets projected to a dimension of model in one operation. Let's trace the shapes carefully, because this is where people get lost. So first, the input size, the shape will be batch size, channel, height and width. If you can see here, in this diagram. So height width, batch size, and number of channels will be the size of the initial image. After applying the convolutional 2D operation, the image will be changed into the shape of dimension of the model, p row, p column, and the batch size. So here p row and p column is the patch row and patch column size. Then we apply flatten on these patches. Then the shape changes to batch size, comma dimension of the model, comma the patch size. And in this case, batch, comma 64, comma 4. After that, we then apply the transpose. In that, the shape changes to batch size, patch size, comma dimension of the model. The final shape is batch, comma number of patches, comma dimension model. This is exactly the same shape as a sequence of token from the language transformer. From here, the rest of the model doesn't know or care whether the input was text or an image. Now let's move on to writing this patch embedding class. Okay, we are back in our coding or Python file. Here we write class patch embedding, and again it will have nn.module as its parent, and for the init function we will have arguments as or parameters as cells, comma dimension of the model, comma image size, comma patch size, and number of channels. And inside the init function, we will first call the init function of the parent class, which is nn.module, and after that we will assign these parameters into variables like self.dModel will be equal to dModel, self.imageSize equal to image size, patch size is that, and channels, all four. Then we will also define a variable that is linear project for linear projection, and that will be equal to nn.conv 2d, and it will have parameters like in channel will be equal to in channel. Let's see if AI has filled it correctly. Out channels is equal to dModel, kernel size and stride is equal to patch size. That is correct. Next, we will write the forward function for this, and again it will have self and x, that is the tensor or image in this case, for as the parameter, and inside that we will first apply the linear projection self dot, basically applying the conv 2d on it on x. Then we will flatten it after applying the conv 2d as discussed a couple of minutes back, and then finally the transpose of 1,2, and finally we will return. Don't worry, I will explain this in a second. Just hold on. I think we are done with this. Yeah, okay, let's go through what this is, what's happening line by line. So first, so these are just assigning parameters into a variable, and next in the nn.conv2d, this is the heart of the patch embedding. By setting kernel size equal to patch size and stride equal to patch size, We ensure the convolutional window moves exactly one patch at a time with no overlap. Each application of kernel covers exactly one patch of the image and produces one dimensional output. The out channel is equal to a dimension of the model, means each patch gets projected to a dimensional vector. The weights of this conv 2D are the learned linear projections. They start random and get trained just like any other weight matrices. Then after that, the x dot flattens everything from dimension 2 onwards. After conv 2D, we have shape of b comma d model comma p colon p row. We want to collapse the two spatial patch dimensions p col and p row into a single p dimension, giving b comma d model and p. That's what x flatten does. After that, the x dot transpose 1 comma 2 swaps dimension 1 and dimension 2, moving d model to the last position and p to the sequence position. We go from b comma d model comma p to b comma p comma d model. This is the format every subsequent layer expects: batch first, sequence second, feature last. And that's it. That's our patch embedding class. Let's move on to the next one. Now we have a sequence of patch embeddings, but we have a problem. How do we get a single classification output from the whole sequence? In the language transformer we built last time, there was no classification task. We were generating one output token per input token. But here we want to look at entire image and output a single class label, like 0, 1, 2 or 9 in this case. One option would be take the average of all patch embeddings at the end and classify that. This works, but it's not what the Vision Transformer paper does. Instead, Vision Transformer introduces a special token called CLS. That is a classification token. This is a learnable vector that gets prepended to the sequence of patch embedding before feeding it into the transformer encoder. It starts as a random vector and is learned during the training. Now, before applying the CLS, we were only passing like patch 1, patch 2, patch 3, patch 4 and so on. But after applying the CLS, we have this additional token as well called CLS token. And then what we are passing to encoder is CLS token, patch 1, patch 2, patch 3 and patch 4 and so on. Now this CLS token goes through all the encoder layer alongside patch embeddings. Because of self-attention, the CLS token attends to every patch and every patch attends to the CLS token. By the end of all encoder layers, the CLS token has aggregated information from the entire image into a single vector, which acts as a global summary. We then take only that CLS token's output and pass it through a classification head. Why a dedicated CLS token instead of averaging? Because averaging treats all patches equally. The CLS token can learn through attention to weight different patches differently depending on what's relevant for classification. It's a learned aggregation rather than a fixed one. The idea actually comes directly from BERT, the language model, which uses the same CLS token trick for sentence classification. And Vision Transformer borrowed it for images. Now let's move on to coding this positional encoding with CLS token. After adding the CLS token, we add positional encoding. Same sine cosine approach as the language transformer. But why do we need positional encoding for images? Think about it. If you shuffle the patches of images randomly, it becomes a completely different image. Patch order carries spatial information. Without positional encoding, the transformer has no way to know the patch 0 is top left and patch 3 is bottom right. One important detail: max sequence length in this case will be n number of patches plus 1. The plus 1 is for the CLS token. Position 0 belongs to the CLS token and position 1 through n patches belong to the patches. The remaining patches basically. So now let's move on to our file and code this class. So we will just write class positional encoding and it will also inherit or have superclass as nn.module, and then we will have init function that will have self comma d model comma max sequence length, and inside the init function we will again call same the unit function of superclass. Then we will have self.cls token equal to nn.parameter, but instead of torch 0 it has to be random because these are learned parameters. I will explain it once I finish writing each and every line. After that we will have the positional encoding or fixed positional encoding, which will be equals to torch.0, same as the previous video. Max sequence length comma dimension model will be its shape. Then for position in range, max sequence length, and for I in range of the D model, we will check if it's an even index. We will assign the sign value to the position PE, POS, and I equal to sign, and the sign value will be position divided by 10,000 to raise to the power of I and dimension of the model, and else we will assign the cost value. Then next we again register add it to the register as a buffer because it is not trained but it is saved in the model. I will explain it in a while, and we also looked it in the previous video, but I will explain it again. Next we'll write the forward function, self comma x is again the input tensor, and inside the forward pass we have batch size equal to x dot size 0, which is the size of the first image batch maybe, and CLS token will be equal to self dot CLS tokens dot expand comma batch size, and then we prepend the CLS token to the batch size using torch.cat, and let's see if AI has written it correctly. No, we do not need this. We add positional encoding to every token including CLS, and then we return the X. And okay, yeah, let's walk through. So this CLS token nn.parameter, this creates the CLS token as a learnable parameter. It's nn.parameter, not register underscore buffer, because we want it trained by backpropagation. It starts as a random noise, and the model learns what values make it a good aggregator. The shape would be 1, 1, D model, 1 token, 1 position, and D model features. And after that, this is simple initializing the positional encoding vector, and in the loop we are again filling that or populating or updating that vector with the sign and cost values. We are registering it buffer, so because it's required in the model. And next, here in the forward pass, this CLS token dot expand, basically the CLS token is shared across the whole model, but we need one copy per image in the batch. So the expand creates a view with the batch dimension filled in without actually copying the data in memory. -1 means keep this dimension as is. Then next, the torch.cat concatenates along dimension 1, the sequence dimension. CLS goes first, then the patches. So position 0 is always the CLS token, and position 1 through number of patches are the image patches. And finally, x plus self.pe adds positional encoding to the entire sequence, including the CLS token. The CLS token get position encoding 0, which is just sine 0 cos 0, sine 0 cos 0, and so on. So the CLS token's initial position encoding is mostly zeros and ones, a known neutral starting point. And that's it. So we are done with the position encoding as well. Let's move on to the next one. Okay, if you watched the last video, you know exactly what's coming here. The attention mechanism is identical. Q, K, V projections, scale dot product, softmax, weighted sum of values. The only difference is that Q, K, V now come from patch embeddings instead of word embeddings. The math doesn't changes. Let me just quickly highlight what's same and what's different before we write it. So in terms of similarity, the formula that is attention QKV equals to softmax of dot product of QK and scaled by the square root of d of k, that then it's multiplied by the value vector. The WQ, WK and WV weight matrices, the scale by square root of dk to prevent vanishing gradient, the softmax over the key dimension. These are the similarities with the language transformer. The difference is there is no masking. In the language transformers decoder, we had a causal mask, so the model couldn't see future tokens. Here in the vision transformer encoder, every patch can attend to every other patch freely. There is no notion of future patches in an image. The image is processed at once bidirectionally. So that's the only difference in the architecture, you can say. And you can see in the image as well that all rest of the things are pretty similar. So let's now write the attention head. So in our file, or in our Python file, we again define a class name attention head. It has ann.module as its parent, and if we have, and in the init function again it will have self comma d model and the head size as the parameter, and it will same thing again call the init of the superclass. It has to be dot and we will initialize self dot wq as linear, wk and wv, 3 linear weight vectors, and in the forward pass it has same input self and x as a torch tensor. We have qkv as self dot wk, wq and wv respectively. In the attention score, we are doing the same. We are we are performing a dot product between q and k, and scaling it with the scaling it with the square root of q, or this has to be not q size. This has to be self dot head size. And the attention weight will be again the softmax of the attention scores with dimension -1, focusing on the features. And the output is again the matrix multiplication between the attention weight and the value vector. In here, the self.wq, wk, and wv projecting from the full dimensional model space down to its head subspace of head size. If we had 8 heads and dimension model of 64, then the head size will be equal to 64 divided by 8, that is 8. Each head operates in its own 8-dimensional subspace and learns a different type of patch relationship. The QK dot product computes the dot product between a query and every query and every key, giving a sequence shape matrix of raw attention score. For our 32 cross 32 image with 4 patches plus 1 CLS token, this is a 5,5 matrix. Every token attends to every other token, including itself. The divide by math dot square root of self head size. This is the same reason like before. Without it, dot product grows proportional to square root of head size, pushing softmax into saturation and killing gradients. And finally, the f dot softmax normalizes across the key dimension, so weight sums to 1 for each query. And the last step, that is the output, produces the final output for each patch position, which is a weighted blend of all values vector based on how much attention was paid. Now, since we have written a single attention head, but as you can see, the transformer is a multi-head attention, so let's write the multi-head attention class next. For that, we will again define a class or write a class multi-head attention with nn dot module as its parent, and in the init function, we pass self d-model and number of heads as the parameter, and we call the super dot init. We assign or define the head size, that is dimension model divided by number of heads. Basically, this line nn dot module list with the attention head and looping through the number of heads creates n heads completely independent attention heads. Here nn dot module list is important because instead of regular Python list, it registers all the heads as submodules of this class. So their parameters show up in module.parameters function and get trained by the optimizer. A plain Python list would not do this. And next, in the forward method, this torch.cat with the okay, I think there is a mistake by the no, there's a mistake. Okay, AI defined it on top. Yeah, so we are first looping it through the number of through all the heads, and basically it runs every head on the same input x and concatenates their output along the last dimension. If each head produces a batch sequence 8 shape and we had 8 heads, concatenation gives batch sequence 64 shape to that output back to the dimension of the model. And finally, instead of self.linear concatenate, this has to be self.w of o and concat. Yeah, this has to be this one. Basically, the output projection, same reasoning as the last time. Concatenation just stacks heads output side by side without any interaction between them. So W weights of output is a fully connected dimensional model comma dimensional model layer that allows every output dimension to be a mixture of every head's contribution. This cross-head mixing is where the real integration of different relationship types happens. Okay, it is complaining something. Oh, okay, yeah. Here I missed something. Instead of n dot linear, this has to be W. Oh, yeah. Now it's fine. Okay, then. So we are done with the attention, our multi-head attention. Let's write the encoder layer next. So for that we will again write a class called transformer encoder layer. This has an dot module again. Okay, let's see if AI writes it correctly this time. Initialization is good. Instead of ff dot hidden dimension, the paper is using MLP ratio, and by default it's 4. And we initialize the super class. We initialize the multi-head attention with the number of dimension of the model and number of heads. There has to be one more normalization layer. As you can see, we have 2 normalization layer. So let's write norm 2. This will be same. Then we write the MLP. AI has made a lot of mistake here. Okay, yeah, now it's correcting it. Fine. The MLP dot sequential, and instead of ReLU we will use GELU this time. I will explain this in a while, just bear with me. And in the forward pass, it first runs. We can write this in a better way like this. X or out equals to X plus, yeah, this is fine. And this will be out equals to out plus self dot MLP, then in which is taking self dot norm 2 of the output as the input, and we return out here. Okay, let's understand what we are doing here. So we have a self dot norm 1 and norm 2 layer normalization, one before each sublayer. In the forward pass, notice the pattern. X dot self MHA with self dot normalize 1 as the parameter or argument. We normalize X first, run it through attention, then add it to the residual. The residual connection bypasses the normalization, so the raw unnormalized X is added back, not the normalized version. Then nn.GELU here, the activation function between 2 MLP linear layer. Basically, GELU approximates X into phi of X, where phi is the cumulative distribution function of the standard normalization. Of the standard normal. In practice, it behaves like a smooth ReLU. Positive values passes through mostly unchanged. Negative values are suppressed, but without the hard zero gradient at negative inputs. And MLP ratio equal to 4. The inner dimension of the MLP is D model star 4. For dimension model 64, that will be 64, then 256 and 64. Similarly, how we did in the language transformer, where we took the in the feed-forward neural network, we took the dimension model from 512 to 2048 to 512. like same 4x expansion. This expansion gives the model capacity to perform complex non-linear transformation before projecting back. And we are then done with our transformer layer as well. After that, we will now move on to the class writing the full architecture. But before that, there is one more thing I need to discuss. So let's dive into our diagram. Basically, after all the encoder layer, we have a sequence of shape batch comma number of patches plus 1 comma d model, but we need a single class prediction per image. This is where this CLS token really kicks in or pays off. We take only position 0, the CLS token's output, after attending to all patches through all encoder layers. This single vector now contain a learned summary of the entire image. We pass it through a single linear layer followed by softmax to get probabilities over 10 digit classes, in our case for the MNIST data. So now let's continue and write our vision transformer class. Again, we will name it a vision transformer nn dot module and in the init function there's one missing. We will we will have self comma d model, dimension of the model, and number of classes, and image size, and patch size. Next is number of channels, number of heads, correct, and next will be number of layers, and final is MLP ratio. By default will be 4. Did I miss something? Nope. Yes, I think I am missing. Oh, okay, a comma here. And what else? Why is it complaining? Okay, we will then again call the super init, and below will be few very simple things. First, we'll store the dimension of the model, d model. Then we will also store the number of classes, and then we will calculate number of patches for each image, or for the image that it will be divided into. That will be image size divided by the patch size multiplied by image size of index 1 multiplied by divided by patch size of index 1. Next, we also set the max sequence length. That will be self dot number of patches plus 1 for the CLS token. And then we initialize the patch embedding class. Embedding, let's see if it has correct arguments. D model, image size, patch size, and number of channel, correct. And post that, we then initialize self dot positional encoding class we created just a couple of minutes before. This will also have d model and max sequence length as input. Post that, the third step will be to have the encoder layers. that will be nn.sequential. Did the air does its job? Let's see. Yep. So this will be the so basically we have 6 layers, so that's why it's in sequence, like one on top of others. So we define each number of layers, in this case 6. For each layer we initialize this transformer encoder layer class stacked on top of each other. Next we have the final classifier that will tell if it's 1, 2, 3. The image is digit 1, 2, 3 up to 9 for the MNIST data. This will be again nn.sequential, nn.linear, a small neural network or network you can say, and the softmax function for classifying. And then we write the forward method. Again, x will be the image, so let's write it images. This will have x equal to self dot, step 1 will be calling the patch embedding on the images basically. Step 2 will be prepending CLS token and add positional encoding, and step 3 is passing through the n encoder layers. And then we are getting the CLS token output as it's always not at position 0. Then the output we send it to the classifier so that it will give us the probability of each image or number. And I think we are done with the vision transformer class. Okay, yeah, that's it. We coded it from scratch, our vision transformer, or basically the paper. An image is worth 16 cross 16 words. One more thing before we close this video. In our vision transformer class, we also need to add 2 assertions. That is first for checking the image size, if it's divisible by the patch size, and also if the dimension of the model is divisible by the patch size, number of heads. So let's add that assertions. I think AI has done it pretty well. Just make it a new line. Yep. And the second one will be demodel. Yeah, these were the 2. There is an issue. Why? Okay. And also I have added the final code for loading and testing the model on MNIST data. So first we convert the image size of 28 by 28 into 32 by 32 because the MNIST is having that size of data. And we resize it into 32 into 32 because our patch size is 16 cross 16, and 28 is not evenly divisible by 16. And in the MNIST data is a data set of 70,000 handwritten digit images, where 60,000 for training and 10,000 for testing. Suppose that we set the train and test set. We then call the data loader to load the data. We then set the device with the if it's running on a CUDA or just simple CPU. Then we call or instantiate our model. Post that we apply the optimizer, or initialize the optimizer, in this case Adam optimizer, and then we take the loss in this case, or criteria, as cross entropy loss. Basically, our model outputs softmax probabilities. So for numerical stability, you would normally output raw logits and let cross entropy loss apply log softmax internally. But for clarity, we keep the softmax explicit here. Next, we run the training loop, where for each epoch we train the model. We initialize a total loss and with 0, and for each imagine level we first uh, 0, like apply optimizer 0 grad. This clears the gradient from the previous batch. PyTorch accumulates gradient by default, so if you don't zero them out, gradient from previous batches add up and you get completely wrong updates. Post that, we calculate the loss. Basically it loss backwards. Basically it computes gradient for every parameter in the model via backpropagation, all the way back through the classifier, through all encoder layers, through the positional encoding, through the patch embedding conv to the weights. And then the optimizer.stab updates every parameter by subtracting learning rate into gradient rate. And Adam does this with adaptive learning rate per parameters. It maintains a running estimate of first and second moment of gradients to scale the update intelligently. And finally, while evaluating, we perform this no grad, because we do not want during the evaluation we do not want the model to learn something from the data. We are just predicting. So while predicting, this torch.max returns both the maximum value and its index along dimension 1. We only care about the index, which class has the highest probability. That index is the model's predicted class. And that's it. That's the training, or testing the R model on MNIST data. You can simply run it. I will share the link in the description. That's the beauty of the transformers. Once you understand it for text, adapting it for images is one clever trick away. That is, treating patches for tokens, and rest everything follows. Link for the code is in the description. Thanks for watching. See you next time.